Let us continue with Schrödinger wave equation, continuing with description of quantum numbers and some rules on electron distribution, what we call electronic configuration. That is the learning objective. Okay. So we've determined that the existence and energy of an electron in an atom is described by its unique wave function psi. Remember again, according to other scientists like de Broglie, Heisenberg, and so many other scientists that describe quantization of energy, including Planck's, they say that we do have energy levels outside the nucleus. If this is the nucleus, I'm not drawing the full circle. Now, an electron can be in N1 or N2 or N3. Those are different, they have different distances from the nucleus, and therefore they will have different energies. And each of these layers is delta E, or change in energy. So the existence of an electron in an atom is described by its unique wave function psi, which of course we say that psi squared describes the volume space where you're likely to find an electron. The word for that, we called it an orbital, and we just described the S, P, D, and F orbitals. We say that the first time you see the S will be in n equals to 1. This first time you see the P is going to be in n equals to 2, so you'll have SP. The first time you see the D will be in n equals to 3, so you'll have SPD. And the first time you see the F will be where n equals to 4, so SPDF. That's what we've discussed so far. Let us learn something new. Pauli Exclusion Principle. It states that no two electrons in an atom can have the same four quantum numbers N, L, ML, MS. No two electrons will have the same quantum numbers. We did the calculations of quantum numbers. No two electrons will have the same quantum numbers. Okay? If that happens, then matter will cease to exist without the Pauli exclusion principle, because we will lose autonomy. Okay? So Pauli exclusion principle states that no two electrons will have the same set of these quantum numbers. Okay, so let's give some definition. This is a structure of an atom. The shell refers to the electrons with the same number of principal quantum number n. So this is a shell, n equals to 1. This is a shell, n equals to 2. The subshell, these are electrons with same value of n and L. For example, if you have 4p, for example, so if you have 4px, 4py, 4pz, they have the same n value, n equals to 4, but we all know that for p, L is always equal to value of 1. All these are called subshells, okay? Because an electron residing here or here or here will have the same n number and the same L number. Remember, L describes the shape of the orbital. It's called the angular momentum quantum number. Number 3, orbital. In an orbital, electrons will have the same values of M, L, and ML. So you'll have the same principal quantum number, same angular momentum quantum number, and same magnetic quantum number. Let me give you an example. So an example of an orbital would be like 1s. Now 1 represents the value of n, the principal quantum number, the energy level, which is found to be 1, and the L value, the angular momentum quantum number L, for s orbital is always 0. Now the magnetic quantum number is always the extreme of L, negative L to positive L, is also going to be 0. You don't have negative 0 and positive 0. So for the values of N, L, and ML for 1s orbital will be 1, 0, 0. Okay, so the only thing that's going to be different for electrons in this orbital is going to be the spin number. One of it is going to be pointing up, the other electron will be pointing down. So in other words, if you have the 1s orbital, maybe this space, one electron points up, one electron points down. So the only difference is going to be the ms. However, N, L, and ML must be the same. And that's what defines an orbital. When N, L, ML are the same for electrons residing in that space called, or the volume called orbital. All right. Now let's show the different energies of these orbitals in a single electron atom, for example, a hydrogen. So we are looking at the energies of the orbitals. Now I'll give you a review. If you have a nucleus, that is our nucleus, representation of a nucleus, and then you have these shells. These shells in themselves contain subshells. The subshells will have their orbitals in there. So let's assume that you have a single electron atom. So the electron will reside somewhere there, but that electron can bounce up by absorbing energy to other energy levels which contain higher level orbitals. So if it's at ground state, meaning n equals to 1, that electron will occupy the 1s orbital, which is this one. The nucleus is somewhere here. Pretend that these are circles. So this is the first energy level, n equals to 1, and this will be roughly n equals to 2, and then this will be roughly n equals to 3. So pretend an electron is here. He can jump up to go to 2s to 2p, depends on how excited he is. So energy only depends on the principal quantum number n, as you can see in my description. The energy of the electron will only depend on the principal quantum number n, whether it's on n equals to 1, n equals to 2, n equals to 3, n equals to 4, etc., going higher outside the nucleus. So the 1s is going to be the one with the least energy, as shown on the y-axis. The y-axis has the label E for energy, followed by usually 2s, then followed by the p's. However, here they are shown to have the same energy, called degenerate, but they're slightly off. Usually you go from the 2s and then the p will be slightly, so just above the 2s, the 2p's will be there. You can see that the second energy level with 2s, 2px, 2py, 2pz is lower energy than the 3s, 3px, 3py, 3pz, and so forth and so forth. So quantization is represented by n, and the energy of an electron in any of these energy levels is dictated only by the principal quantum number n. Okay. Now, if you have this is what I was telling you. If you have multi-electron atom, you see that there is a lot of difference in energy because now you have more electrons. So let's say you have more than enough electrons. Let's say you have 2 electrons in the first energy level. So let's call this 1s2, where 2 represents the 2 electrons. Then let's say you have 2 electrons in the 2s, 2s2. By the way, the s orbital carries a maximum of 2 electrons. And then from there you're going to go to 2p6. Okay, so there you have 3 sets of p's, so each of those will carry 2 electrons, so the p orbital generally will carry 6 electrons. From there you go to 3s2, 2 implying is carrying 2 electrons, then 3p6, because we are assuming we have a lot of electrons, the p orbital carries 6 and each 2 electrons must be paired. Then from there again you go to 4s, and the story goes on and on and on. So you see in the multi-electron atom, the 2s and the 2p are separated, they are not degenerate. But here in the single electron atom, like a hydrogen gas, assume there are no electrons up here, assume that the electron is just but at n equals to 1, you will see that these guys are degenerate. The 2s and the 2p's are on the same energy level. We call that degenerate. So in many electron atom, they split up. The 2s and the 2p's will split. The 3s and the 3p's will split. They have different energies. The 4s and the 4p's are even split even further. The 3d will come in between. Okay, so there are rules for filling up these electrons from the lowest energy to the highest energy. The more you go away from the nucleus, going up from n equals to 1, n equals to 2, n equals to 3 approximately, n equals to 4 approximately, the energy is increasing. So the topmost level has the highest energy and the bottommost level has the lowest energy. What did I call the lowest energy? Ground state, where the electron is very happy and stable. He's close to the nucleus, he's strongly attracted to the nucleus, he's very happy. So there is a scientist called Aufbaus that helped us by explaining the order we should follow in filling up electrons from the one with the lowest energy to the one with the highest energy. So if you're given, let's say, 4 electrons, maybe I should look at the case of who? I think beryllium. Beryllium has 4 protons, 4 electrons. So I'll start by filling up the bottom, and the ms value plus a half minus a half must be followed, because no 2 electrons must have the complete set of quantum numbers. Remember we said that the 1s has n equals to 1, l is 0, and then ml is 0. Surely something has to be different. That would be the ms. So one will have plus a half, the other one will have negative a half, just because it's facing down. So that is Pauli Exclusion Principle. But now Aufbaus Principle is telling me if I have a lot of electrons to spread, I should fill from down. So I've used 2 out of the 4. The next 2 will go to the 2s. Okay. Now an element like carbon has 6 electrons, and so I will find a way to spread the other 2 here without pairing. That is another rule coming up. I think it's called Hund's rule. Okay, we'll talk about that. Let me leave this example of beryllium here for now. And here comes Hund's rule. Hund's rule states that the most stable arrangement of electrons in subshell is the one with the highest number of parallel spins. Okay, the one with the highest number of parallel spins will be the most stable arrangement. In other words, you're maximizing the spin. Let us see an example here. Let's use the example of carbon. Carbon has 6 electrons. Now, just to go ahead of myself, the rule here, before we arrange the electrons in a manner called electronic configuration, the rule of spreading these electrons in electronic configuration is this. One of them is Hund's rule. Of course, we talked about Aufbaus, but I want to give you the general rule. So for the s orbital, the maximum electrons it carries is 2. For the p, the maximum electrons is 6 electrons in p orbital. And then for the d, he carries a maximum of 10. F will carry a maximum of 14 electrons. So alongside of Aufbaus principle, Hund's rule, or Pauli exclusion principle, you want to really know this golden rule of how many electrons can maximally be found in SPDF. So S will always carry a maximum of 2 electrons, no more than 2. But of course, if you want to follow Aufbaus principle, Pauli exclusion principle, that no 2 electrons can have the same quantum numbers, it will mean that one electron will point up, one will point down, so that their ms values will be different. Okay, so now if I'm looking at carbon, if I have to write the electronic configuration of carbon with 6 electrons, we have to fill from the one with the lowest energy. Remember, there is 1s, 2s, 2p. This is a multi-atom element. From 2p is 3s, then 3p. Okay, so that means I'll give my 1s 2 electrons, opposite spin, 2 electrons for 2s, and when I get to p, he carries a maximum of 6. So far I've used 4 electrons here, so I'm left with 2. So there will only be 2 in the p orbital. The question is, will they both point down, point up, be in the same suborbital, meaning px, py, pz, or will they be different? I think 1s and 2s are filled up already, so the other 2 electrons goes to the 2p, and the question is, how are we going to arrange them? Will you do A, will you do B, or will you go with C? Which one of these follows Hund's rule, which states that the most stable arrangement of electrons in subshell is the one with the greatest number of parallel spins? Greatest number of parallel spins has to be C. Remember, they cannot be in the same box. I can even add another option here. This is px, py, pz. So suppose I put them like this. Is that correct? No. While both of them are facing the same side, which is the spin, while both of them are maximizing the spin, they are in the same orbital with all same quantum numbers. So in this case, let's call it D. In case D, where the electrons are in the same orbital and both pointing up, N is 2 because they're in the second shell. Remember, we are focusing on this, 2p. L will be 1 because they are in the p orbital. And then ML will be -1, 0, +1. All of them will share all this. Okay? And then when you go to MS, it will be +1/2 because they are both pointing up, so nothing is differentiating them, and this is failing Pauli exclusion principle, which states that no 2 electrons in an atom can have the same 4 quantum numbers. See that? So which is why option D here is wrong. This one is not maximizing. How is this not maximizing? You know, this is maximizing. D is maximizing because +1/2, you're going to get the answer as 1. But for option A here, the one pointing up is +1/2. If you add it to the one pointing down, -1/2, so it's like +1/2 minus 1/2 is 0. We are not maximizing. Same thing here, we are not maximizing because this is +1/2, this is -1/2, that's 0. However, here, the 2 electrons, these arrows are electrons, I told you so many times, the 2 electrons are both pointing up, So the first one has an ms magnetic spin of +1/2, the second one +1/2. They are not in the same box, same orbital, so this is correct, which is why we would draw them like that in the energy diagram. So the electronic configuration of carbon, electron arrangement of carbon would be 1s2, 2s2, 2p2, where these 2's are the number of electrons in carbon. If you add 2 plus 2 plus 2, you're going to get 6 electrons, which is what you have in carbon. So I think I've explained that at length. Maximize your spins. Let's try another example. Remember again Hund's rule, the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. Okay, so we have to maximize parallel spins. So nitrogen has, I believe, 7 electrons. So definitely I want to draw the box for 1s and another one for 2s. We are filling from the one with lowest energy, and then from there I need my 2p. They are usually 3 boxes or three subshells within the 2p. So here you're going to have 2 electrons of the 7, and then here you'll have 2 electrons of the 7. So far those are 4 electrons. You have to pair them, but with opposite spin, ms -1/2, ms +1/2. I'm left with 3 more. So for the 3 more, I will put them like that, not like that, not even like this. Remember Hund's rule, you're maximizing parallel spins. This is not good, this is not good. Not even putting 1 here and 2 skipping this empty. That's not good. Remember, one of these is px, the other one is py, the other one is pz. This is good because each of those is pointing up. So +1/2, add to +1/2, add to +1/2, you're going to get 1.5. These ones, if you add them up, they'll never give you 1.5 because the arrow pointing down is -1/2, and we're taking the arrow or the electron with upward spin, we are taking it to be +1/2. So that is the correct drawing of energy diagram, electronic arrangement of 7 electrons in nitrogen. Fluorine has 9 electrons. So I think 1s2 will take 2 electrons. The 2s will take 2 electrons. Remember, s carries a maximum of 2, p carries a maximum of 6, d carries a maximum of 10 electrons, f carries a maximum of 14 electrons. I'm left with 5. In that case, I'm gonna get to the p orbital, the 2p. One of these is px, one is py, the other one is pz. Each carries a maximum of 2, so that the entire 2p can carry a maximum of 6. But you are left with only 5. We've accounted for the 4 in 1s2 and 2s2. So firstly, I'll have to singly populate them because I'm trying to maximize my spin. Then I start pairing. So far, I have 7, like what we had in nitrogen. And then I pair up like that. See, you're left with one that has +1/2. That's good. That's the application on Hund's rule.